Now just tell me, are you able to see the screen? Now is it fine?
Yes, sir.
Okay.
Yeah.
Okay. So my voice is audible to all. Is it fine?
Yes, sir.
Okay. Good. Thank you. So let's understand the topic thermodynamics. It's a chemistry class 11 topic. It's a very important topic for all because it carries huge weightage in your competitive exams as well as board exams. So what are the concepts you are going to understand in this topic? First law of thermodynamics, change in enthalpy, bond enthalpies, heat capacity and specific heat, Hess law, entropy change, Gibbs energy, as well as third law of thermodynamics. So let's understand these terms and concepts one by one. Before we start, I just want to let you know what is the meaning of thermodynamics. I just want to define what is thermodynamics. What is the meaning of thermodynamics? Thermo means heat and dynamics means flow, or you can say motion. So whenever there is a flow of heat in physical and chemical reactions, at that time we can say that the concepts of thermodynamics are been involved. In physics you must have understood that work is done, or you can say whenever there is an energy transfer, we can say that work is done. So for thermodynamics, that energy transfer is mainly for heat energy. Over there you can see in the second point, the systems related to the usage of heat for doing work, means usage of heat energy for doing some work, and that whole concept is thermodynamics. Let's understand broadly system and surrounding. Okay, so very important concept. What is system now? In the first point you can see the definition of system: the part of universe in which observations are made, or in which is under investigation, is called system. On the right you can see a picture. I have a piston cylinder system. I have a piston cylinder, and inside the cylinder I have gas molecules. Okay, inside the cylinder I have gas molecules here, and the system and the surrounding are separated using a boundary. Now what is a system? The part in which observations are made, or which is under investigation. I mean, we are going to do all the thermodynamics, all the thermodynamical, all the terms will be used for this particular system, for these gas molecules. So this is under investigation, under observation. So this is your system. And what is the surrounding? The part of the universe other than the system is your surrounding. So what we can say, universe is equal to system plus surrounding. Okay, and both the system and the surrounding are separated using a boundary. It can be real, it can be imaginary. Here you can see a real boundary. There will be questions where you will have to like figure out what is the boundary, means that would be imaginary. We will do such questions. Okay, I hope it is clear, system and surrounding. Let's move ahead. Now coming to what are the type of systems. Okay, so basically speaking, there are three types of system: open, closed and isolated. Let's understand this broadly. What are open systems? Here again, I have taken a test tube, I have taken a system. Okay, I have considered surrounding, means the part of the universe other than the system is your surroundings. Okay, I have a solution inside a test tube. And now why I'm saying this open system, because first thing, there is no lid, it is not closed, right? It's open, so we can transfer matter. Means if I want to transfer some matter, if I want to add a matter inside this test tube, I can easily add. Means matter can be easily exchanged from the surrounding to the system. Okay, and let's discuss about energy. What is energy? If I start heating this from below, okay, what will happen? The heat will be transferred to the system, and we can see vapors coming out from the system. Okay, so what is happening? The system is getting heated up. So there is an energy transfer from the surrounding to the system. So open system is when we can transfer matter as well as energy, both the things. Now what is closed system? Closed systems are nothing but matter is not transferred but energy is transferred. I mean to say that this test tube is closed from the top. Okay. Now can I add a matter to this? No, because it is closed now. So matter can't be transferred, but energy can be transferred. How? If I start heating this from below, what will happen? Again, the energy will be transferred, because here it is a conducting wall, you can say, or you can say a conducting boundary. So the energy will be transferred from the surrounding to the system, and this system will be heated up, and we can see the vapors coming out. Now coming to isolated system. What are isolated system? Again I have defined system and surrounding. I have taken an insulated wall over here, or insulated boundary. As I said, what is a boundary? You can say it separates system and surroundings. So I have taken an insulating boundary. Now isolated system are the system where matter and energy both are contained. What is the meaning of contained? I mean to say that nor matter nor energy can be transferred from surrounding to the system. Again, it is closed from above. The matter can't be transferred, and energy cannot be transferred. Why? Because if I start heating it, my boundary are insulated, so this heat energy won't be transferred from the surrounding to the system. You can take the example of the flask, thermo flask. Okay, whatever is there inside the flask, if it is hot, it will remain hot, and if it is cold, it will remain cold. Okay, so such type of systems are isolated systems. Let's summarize it. Open system, matter and energy both can be transferred. Closed system, matter can't be transferred but energy can be transferred. Isolated system, neither matter nor energy can be transferred. Okay, I hope it is clear to all.
Yes, sir.
Good. Let's move to the next slide. State of the system. What is the state of the system? Let's understand. So whenever I discuss about the state, I am talking about a system. I am defining system in terms of measurable properties such as temperature, pressure and volume of the system. Okay, so here on the right you can see two pictures, before and after. Before means initial state. So if I am talking about state, I am talking about the temperature, pressure of the pressure and volume of the system. Okay, so I can say that if it is initial state, the temperature is T1, the pressure is P1 and volume is V1. And after some interval of time, again the state will change. So now the temperature will be T2, pressure will be P2 and volume will be V2. Okay, so that is how you define the state of the system in terms of measurable properties. Okay, at the bottom you can see for an ideal gas enclosed in a piston cylinder system, P1 V1 by T1 equal to P2 V2 by T2. So where does this formula come from? It actually came from an ideal gas equation. What is an ideal gas equation? PV equal to nRT. What is P? The pressure, V is the volume, N is the number of moles, R is the gas constant and T is the temperature. Okay, so what I will do is, I have taken a system, it is closed, it is a closed system. Okay, so my mass of the gas which is taken inside the system is constant, or you can say moles is also constant because mass is constant. So PV equal to nRT. So if I take temperature on the left hand side, what I can say, PV upon T equal to N into R. PV upon T equal to N into R. Therefore PV upon T equal to constant. So any state, take it any state, PV upon T will always be constant. So that is why I have written over here P1 V1 upon T1 equal to P2 V2 upon T2. Over here you can see P1 V1 upon T1 equal to P2 V2 upon T2. Because my moles and the gas constant Both the terms are constant for me. Okay. Now, what are state functions and path functions? This is a very important concept for you to understand. The properties whose values depends on the state of the system. See, state functions, the name is only saying it is something related to the state of the system. Okay, and path functions, the name is showing that it is something related to the path. Okay, so let's understand state function. It depends only on the state of the system, be it initial and final, and not how it is reached. Okay, so let's take an example of a system. The initial state is P1 V1 and the final state is P2 V2. Now this terms pressure, temperature and volume, these are all the state functions. Why? Because we define, what do we say when we say that the state of the system? We define it in terms of pressure, temperature and volume. Okay, even internal energy, enthalpy and entropy. We will understand these terms in the coming slides. Okay, so whenever I say state functions, I mean to say pressure, temperature and volume, because they all are dependent on the state of the system, be it initial and final. Initial means P1 T1 V1, final means P2 V2 and T2. Let's understand what are path functions. That depends on the path taken to reach one state from another. Those functions that depend on the path taken to reach one state to another. Over here you can see initial state to final state. There are three paths: path number 1, path number 2 and path number 3. Now what are state functions? Pressure, temperature and volume. Means we have defined initial state and final state for them. You take any path, 1, 2 or 3, doesn't matter for state functions. What matters is what is the state. And for the path function, the path does matters, that whether you take path number 1 to reach final state from initial state, whether you consider path number 2 or path number 3. So what are the examples of path functions? Heat and work. Okay, they are energy transfer. They are not intrinsic to the system, because we don't define heat and work for the state of the system. They are just the energy transfer. Means we can't say that the heat of the system, heat of the system right now initially is this much, or we can't say that the work of the system right now at T equal to 0 is this much. Okay, it's just the energy transfer taking place. And that is why they are path functions. Okay, I hope you understood. Let's come to next topic over here, subtopic extensive and intensive properties. What are these? So extensive properties are the properties that depend upon quantity of matter present and are additive in nature. What does it mean? Let's say volume. If I have taken a test tube over here, there is volume V1, and if I add, I have taken a test tube here, or you can say a beaker over here, the volume is V1, volume of the solution is V1. Now if I add volume V2, can I say that the final volume will be V1 plus V2? Yes. So these properties, I mean to say volume is additive in nature, and these are extensive properties, and it depends on the quantity of matter. Okay, volume is the quantity, 500 ml, 1 liter, 2 liters. Same for mass. Mass is again depends on the quantity of the matter, and yes, it is additive. Right now if I say volume is V1, if I again say the mass is M1, and I can add mass M2, so the net mass will be M1 plus M2 inside the beaker. Okay, now intensive properties, the opposite of this, that do not depend upon quantity of matter and are non-additive in nature. Let's say density. Let's take an example of density. Here we have a solution over here, density ρ1, and I again add another liquid of density ρ2. I can't say that the final density is ρ1 plus ρ2. Okay, because density are non-additive in nature. These are the examples. Again, temperature as well. Right now the temperature of the system is T1. I mean to say that right now whatever is there inside the system, or whatever is the system, the temperature is T1, and if I add another solution of temperature T2, can I say the final temperature will be T1 plus T2? No. So these are non-additive in nature. Understand, intensive, non-additive, and doesn't depend upon the quantity of matter. Extensive, depend upon the quantity of matter and are additive in nature. Okay. Now this is very important. Internal energy U. What is internal energy according to you? See, again, same thing. In thermodynamics, this is how you will define a system. You will take a gas, a piston cylinder system. Inside the cylinder, there will be gas molecules here. Now, what is internal energy? The energy possessed by the system. I mean to say that the total energy possessed by the system, be it chemical energy, electrical energy, mechanical energy, is your internal energy. And yeah, see the second point, we can't find the absolute value of U. What is right now the total energy of the system cannot be determined. But we can say that if I start heating this, particular system, what will happen? Just assume that this boundary is conducting, the conducting boundary. What will happen to the gas molecules? The temperature will increase. Okay, the temperature inside the cylinder will increase, and at that time we can say that the internal energy of the system has increased. Why? Because the gas molecules will start vibrating to and fro from their mean position. So if the kinetic energy will increase, we can say that yes, the total energy will increase. Okay, we can't actually find the absolute value of internal energy, but we can find the change in internal energy, delta U. And how it is denoted? It is denoted by delta U, which is equal to U2 minus U1. Okay, change in internal energy, delta U equal to U2 minus U1, and it is primarily the function of temperature. If the temperature will increase, I will say that the internal energy of the system is increasing, and if the temperature will decrease, I will say that the internal energy of the system will decrease. Let's move to next slide. Let's understand what is heat. How I denote heat? By the letter Q. Okay. Now again same thing, system and surrounding. I have taken a beaker over here. I have taken system. There is a matter inside, and other things than the system are your surroundings. Okay. So let's understand, the temperature of the system is TA and the temperature of surrounding is TB. Now this you might have understood in your previous classes, that heat is transferred from, that there is a transfer of heat from higher temperature to lower temperature. So now let's assume case number 1. The temperature TA, I mean to say that the temperature of the system is higher than the temperature of the surrounding. So where will the heat transfer? From system to surrounding. Why? Because the temperature of the system is higher than the temperature of the surrounding. So it will transfer from the system to the surrounding till there is equilibrium. And what is equilibrium? When both the temperatures are same. Again, case number 2. If the temperature of the surrounding is more than the temperature of the system, we can say that the heat will be transferred from surrounding to system till there is equilibrium, which is TB equal to TA. Now you need to understand these sign conventions. These are very important. If heat is transferred from the surrounding to the system, yes, if it is transferred from the surrounding to the system, let's say if I hit this, if I start heating this, the heat is transferred from the surrounding to the system, and at that time I will say that my heat is positive, it's plus Q. And what are the reactions known as when the heat is positive? It's endothermic reactions, where heat is transferred from the surrounding to the system. Those are endothermic reactions. Now let's see the other part, case number 2. When heat is transferred from the system to the surrounding, I take Q as negative, which are exothermic reactions, and that results in the decrease of the internal energy of the system. Okay, let's understand further what is work W. So work is nothing but it is the process done by or on a system. Okay, and that is how the system and the surrounding will interact. That is how the system and the surrounding will interact and exchange energy. So if they exchange energy, what was the first line? There is exchange of energy. Which energy? Heat energy. There is exchange of energy, and that is thermodynamics. So there is exchange of energy. I mean to say that the interaction is taking place between the system and the surrounding, and that process is your work. Okay, let's understand the ways how to change the state of the system. Let's see mechanical work. See here what I am saying. Again, I have taken a piston cylinder system. There are gas molecules inside this, a matter inside this in a system. Now there are two ways to increase the internal energy of the system. I can do shaft work. I mean to say I have set up a set of small pedals over here. If I start rotating this, what will happen? This kinetic energy will be transferred to heat energy, and the internal energy of the system will increase. So what I am saying, work is a process done by or on a system. So here work is done on the system by the surrounding. So there is interaction between the system and the surrounding, and there is exchange of energy from the surrounding. I mean to say that the exchange of energy, what does it mean? There is an exchange of energy from the surrounding to the system. And what is the second way? Electrical work. That was mechanical work initially. This is electrical work. Again, I have set up immersion rod here. What will happen now? Due to this rod, I mean I am connected to a power supply. Now this rod will start heating, and again it will heat the gas molecules inside the system. And if the temperature of the system will increase, what did I say? The internal energy of the system will also increase. Okay, so thing to be noted over here, sign convection. If work is done by the system, we say negative work, and if work is done on the system, we say positive work. Okay, and these two examples are work is done on the system by the surrounding. So these two work are positive works. Okay, let's understand further. See, again same, discussing about PV work. What is P? Pressure. What is V? Volume. If energy enters the system from the surrounding, its sign is positive. This is what we learned in the previous slide. If energy is added to the system by any means, by mechanical means or electrical means, from the surrounding, if it is added to the system in terms of heat energy over here, which increases the internal energy of the system, at that time we say that my work will be positive, its sign will be positive. Okay, and what is the another case? If energy leaves the system, its sign is negative. If work is done on the system by the surrounding, the work is taken positive, and work is done by the system, its sign is negative. Or you can also say that if it is an expansion, here again, here is a gas, I have started heating it. Okay, so what will happen now? This piston will move above. Why? Because I have heated this from below. So this piston, which is a movable piston over here, and there is a mass inside, mass above, that is providing external pressure. So if I start heating the gas, the piston will move above. There is an expansion taking place. There is an expansion taking place over here. So due to expansion, we can say that work is done, and that work is taken as positive. Why? Because work is done on the system. And again, if there is compression like this, okay, I say that the work is negative. P external equal to P internal, I say that it is equilibrium. If P external is greater than P internal, I say that the work is done on the system, and if internal pressure is higher than external pressure, I say that work is done by the system. You can understand like this. P external means this is the external pressure. Okay, so if P external is greater than P internal, you can say the case of compression. You can say the case of compression means this is the first initial state and this is the final state. The P external pressure is more than the internal pressure. This piston will move down. Hence, we can say that work is done on the system. And if internal pressure is more than external pressure, I mean to say that the pressure of the gas inside this is more than the pressure, the external pressure provided by this mass M, this piston will move up and there will be expansion taking place. So now, who will be doing work? The system. So work is done by the system. Okay. I hope this is clear to you. And what is the formula to calculate work? Very important. Minus P external times delta V. What is delta V? Delta V equal to V final minus V initial. Now it is not necessary that V final will be more than V initial. It depends on the process which is taking place. V final minus V initial. What is the final volume and what is the final initial volume and final volume? That is how you define delta V. Delta means change in volume. Now, very important concept, first law of thermodynamics. Understand this very carefully. For a closed system, see closed system. What is closed system? The matter can't be transferred, but energy can be transferred. For a closed system, the internal energy is essentially defined by delta U equal to Q plus W. Delta U, what is delta U? Change in internal energy. What is Q? Heat. And what is W? Work done. Okay, and this law is nothing but it is known as the law of conservation of energy. That is, energy can neither be created nor it can be destroyed. Let's understand this. Where does this formula come from? Let's say a system is right now at an initial state, or we can say initial state means pressure is P1, volume is V1 and temperature is T1. If its temperature is T1, I can say that the internal energy is U1. Now I am providing heat to the system. I am heating the system. Heat energy is transferred from surrounding to the system. So addition of heat energy. What will happen now to the energy of the system? Initial plus this plus Q. Law of conservation of energy. So what will happen? What is the final energy right now here at the second stage? U1 plus Q. Now if I start doing work on the system, it can be a mechanical work or it can be a electrical work. Now the final state will be U2. What does U2 define? The temperature is T2. So I can say that if the temperature is T2, definitely the temperature will change. If you are adding heat to the system from the surrounding and if you are doing work, the temperature will change. So final state I can say U2. So again, U2 will be equal to U1 plus Q plus W. U2 equal to U1 plus Q plus W. Conservation of energy. This is nothing. This is just the law of conservation of energy. Now if I take U1 over here, it will be U2 minus U1. And what is U2 minus U1? Delta U. U2 minus U1 is delta U equal to Q plus W. Okay. So simply the law of conservation of energy, which is your first law of thermodynamics. Now I want you all to do these important questions right now. These are the part of the NCERT exercises and very important questions for all. Let's read question number 1. In a process, 701 joule of heat is absorbed by a system. Understand this. This is very important. Absorbed by a system. And 394 joule of work is done by the system. What is the change in internal energy for the process? So anyone who would turn on the mic, who can speak? How will you solve this question? which formula are you going to apply, or which law you are going to apply? You just learned right now, delta U equal to Q plus W, right? So you need to find internal energy over here. What is Q? 701 joules. But as per the sign convention, is it positive or negative? Now heat is absorbed by the system. Let's see the convection. If heat is absorbed by the system, means heat is transferred from the surrounding to the system. So that Q is positive. Okay, so I can take this as plus 701 joules. If I want to use this value in the law, I will take this as plus 701 joules. Unit is important, see, joules. Okay, and what is the next part? 394 joule of work is done by the system. Now work is done by the system. If work is done by the system, its sign is negative. So I can't take value 394 as it is and put it in this law over here. What value I will take? Minus 394. This one plus 701, and then I will put over here the values and I will find the internal energy. Very simple question, but again, the importance of sign convection. Now the second question, express the change in internal energy of a system when no heat is absorbed by the system from the surrounding but work is done on the system. What kind of wall does the system have? See, no heat is absorbed by the system from the surrounding. Okay, so I can say it's a isolated system. So what kind of wall it would be? Insulating walls, I can say. Okay, because heat is not transferred from the system to the surrounding, not surrounding to the system. We take the example of thermoflask. No work is done on the system, but no amount of heat is taken out from the system and given to the surroundings. What kind of wall does the system have? See, heat is transferred, so I can say that the wall would be conducting wall. Okay. Now let's understand what are the different types of processes in the thermodynamics. What are the different thermodynamic processes? Isobaric process, isochoric, isothermal and adiabatic. All of them have a different significance. If I say isobaric process, it means throughout the interchange of energy taking place, or throughout the process, I can say, throughout the thermodynamic process, the volume will remain constant. Whose volume? Let's understand once again. Let's take piston cylinder system. Let's take this piston cylinder system. Again, gas is there inside the this cylinder. This is initial state. Again, in the final state, I will say that the volume of the gas. What is volume of the gas? This much part. It will always remain same. You can take the example of pressure cooker. Take the example of pressure cooker. What is happening? The volume is constant, but whenever you are transferring heat to the system, the pressure will increase, isn't it? And due to the increase in the pressure, the food which is raw will be cooked now after some time. So such type of systems are known as isochoric processes. Such type of processes are known as isochoric processes, where the volume is constant. Now coming to isobaric process, what are isobaric processes? The pressure will always remain constant throughout, in the initial and the final state. Isothermal, the name is only suggesting it. Isothermal means the temperature is constant throughout. And adiabatic, heat is zero. Heat transferred is zero. Okay, adiabatic means heat transferred is zero. Heat transferred zero means from system to the surrounding. No, it has been transferred. So those are adiabatic processes. Let's summarize it. Isobaric, constant pressure, as I said. So work done would be minus P delta V. Isochoric, constant volume. So work done is minus P delta V. Now the volume is constant, so delta V is equal to 0. Hence, you can say that the work done is 0. Isothermal, constant temperature, delta T equal to 0. I can say that delta U is also 0. Adiabatic, no heat transfer, Q equal to 0. So that is the summary. Now let's understand what are reversible and irreversible processes. A reversible process proceeds infinitely slowly by a series of equilibrium such that the system and the surroundings are always in near equilibrium with each other. What does it mean? The system which you have taken and the surrounding, they should always be in equilibrium to each other. Like let's take initially, let's understand with an example. Initially, again same piston cylinder system, there is a gas, state number 1, state number 2. Now if that process would be reversible, what will happen? Initially they moved from state number 1 to 2. Now when they will move back from state number 2 to 1, they will follow the same path. The system and the surrounding will follow the same path. So such type of systems are reversible systems. And what is the another one? Irreversible processes. Okay. So from 1 to 2 is this process, and from 2 to 1 the path followed would be this. From 1 to 2 for irreversible, from 1 to 2 would be this, and from 2 to 1 it would be like this. So such type of systems are irreversible systems. You can take the example of pressure cooker again. Okay, so that system, I mean that process is irreversible. Why? Because now the raw food that was there initially at the initial is now cooked. Can you like convert, I mean can you like change the cooked food into raw food? No. And what is that process? The volume is constant, so isochoric process, and that process is irreversible in nature, because now you can't I mean to say you can't change the cooked food to the raw food back. So those are irreversible. And what are reversible? See, at each and every interval of time for the reversible process, the system and the surrounding will be in equilibrium for small intervals. So throughout we can say that the system and surrounding are in equilibrium to each other. So whenever we change the path from state 2 to state 1, I can say that the path followed would be same as followed initially. So these are reversible and irreversible processes. Now for the reversible process, let's understand work, PV work. So what was the formula for work? Minus P external times delta V. And again we know that for the reversible process, I mean the system and the surrounding should be in equilibrium to each other. So for that condition to be fulfilled, it is required that the external pressure should be equal to internal pressure. Not exactly equal, but near about they are equal to each other. P external equal to P internal. Okay, so what I can see over here, work done equal to minus P times delta V. Now this P is P internal, which is pressure of the gas, okay, and you will know what is the ideal gas equation. PV equal to nRT. So if I take this volume on the right hand side of equal to, pressure P equal to nRT upon V. Okay, I can also say that over here, work done equal to integration of minus pressure times dV. and if it is dV, I am applying limits over here, V initial to V final. So this is a general formula for work here. Now this pressure P is pressure of the gas. Okay, why pressure of the gas? Because P external equal to P internal. So external pressure equal to internal pressure. What is it? Internal? The pressure of the gas. Because gas is the system now. So further solving this, I am substituting this value P equal to nRT by V over here in place of P. Minus of integration nRT upon V times delta V from V initial to V final. Okay, now this moles, gas constant and temperature all are constant. So I'm taking this outside this integration here. So what is left inside the integration? Delta V upon dV upon V. It's dV upon V. Okay. So what is integration of dV upon V? Minus nRT ln V from V initial to V final. Okay. So while solving this, it's minus nRT ln V2 upon V1. So this V2 and V1 both are inside this ln. So I can say that if I want to remove this ln and convert it to log, what is ln? Log to the power e, log to the base e. I'm sorry, it's log to the base e. So I just want to convert this log to the base e to log to the base 10 because that is widely used. So I add the constant over here. There is a factor 2.303. 2.303 nRT ln got converted to log, so I am writing over here log V2 upon V1. Okay, so this is the formula for work done in a reversible process. Very important formula. Minus 2.303 nRT log V2 upon V1. Okay, sometimes in boards it is frequently asked. They give you the moles, they give you the temperature of the system, they give you the change in volume. Directly you have to use this formula and get the answer. So learn this formula, very important formula. And I have added a question for you all based on the same formula. It's an isothermal process, means temperature is constant. Again, reversible process, work done. You have to calculate. Moles are given to you, and it's mentioned that the gas, it's an ideal gas which is expanded so that its volume is doubled, and the temperature is also given 400 Kelvin. So how will you solve that? Again, use the same formula. Work done equal to minus 2.303 nRT log V2 upon V1. Now what is this V2 upon V1? As per the question, now its volume is doubled. So my V2 is 2 times V1. So what is V2 upon V1? It's equal to 2. Okay. And what would be the moles? It's given to you. How much are the moles? 5. You just have to put the values in the formula. Moles is 5. The temperature is also given 400 Kelvin. Remember this thing. Okay. You always have to take temperature in Kelvin. See, formulas is okay, fine. I give you the formula. but you should understand how to use the formula correctly. And how to use the formula correctly, what does I mean to say with that statement? You have to see that there is consistency in the units. Here I will take SI units. So for the temperature, what is the SI unit? Kelvin, not degree Celsius. So it's already Kelvin is given to you. So you just straight away put the value of 400 here in the formula. And what is the value of R? The gas constant in terms of SI units, 8.314. Put that value. Again, the units are SI units for this. So moles RT log 2. So once you calculate this, you will get the answer. So tell me what is your answer in the comment section. Okay, the video will be live on YouTube. It will be uploaded by tomorrow. And again, I will share you the PPT because I don't think so you might have written the notes. And it was just meant for you to understand right now. And you can make the notes. The PPT will be shared to you, and this video will be live on YouTube. I just want all of them to, comment the answer of this particular question. Okay, so just note down the values. Note down the values. Moles is 5, the volume is doubled, and the temperature is 400. Solve it on your own. Don't use the calculator and get the answer. See, the answers are in kilojoules. The options are in kilojoules, and answer which you will get will be in joules. So one extra step you have to do is convert joules to kilojoules. Okay, so I'm giving you the hint. You just have to divide this value by 1000 to convert from joules to kilojoules. Okay, just do it at your home, at the values, and tell me the answer in the comment section once the video is uploaded on YouTube. Okay, thank you so much everyone. Thank you for listening. I hope you understood the topic. We'll continue in the next class. Thank you. Bye bye.